about bounds on polynomial volume growth of automorphisms of zero entropy.
Okay, thank you. Thank you very much for the invitation. So it's my great pleasure to speak in this workshop in Moscow, although just online. So today I'm going to talk about this journal work with Chen Jiang from Fudan University. Actually, I just slightly changed the title, so because it's a talk in Moscow, I guess this name is better. So I'm going to talk about upper bound for scaffold Kirchhoff dimensions of automorphism of zero entropy. So actually, this is equivalent to the previous one. The previous is a polynomial volume growth. So these two invariants are equivalent. So actually, the only difference is just one. So as you will see later. So in this talk, so the first part, I'm going to discuss some background of this problem, and then I will discuss some knowing results, and then I will talk my our journal work. So first of all, let me start with the so-called algebraic dynamics. Okay, so for a algebraic dynamical system, so actually this is just a pair, so not this kind of pair. So X is a variety. So in this talk, so I just focus on variety defined over C. So actually, our result also works in positive characteristic, but for simplicity, let's say X is a smooth projective variety, complex variety, and F is a surjective endomorphism. And I also always use this D to denote the dimension of the ambient variety X. Okay, so for this system X, comma F, so one of the most important invariant for this system is so-called topological entropy. This so-called denoted by H top F. So I won't define this entropy in this talk, but the original definition is very analytic. I guess it's also due to Roger score in 50s or 60s. So for example, by Arnold score. So the definition is very analytic. So for example, it uses some double limit to, and also use some in so-called induced metric on this associated complex manifold. Anyway, so roughly speaking, it measures the complexity of the system, but in practice, it's not easy to compute this quantity. However, so fortunately, in by Grumov's work in 70s and later by Yomedin's work in 80s. So now we know that this topological entropy originally defined in a very analytical way. So this invariant turns out to be equivalent to another algebraic invariant. So right hand side, this is called I use H-ag of F to denote this so-called algebraic entropy. It is defined by now I can define this invariant. So it is actually the logarithm of the spectral radiance. So I use rho to denote the spectral radiance of some linear operator. So consider the pullback action of F, this is surjective endomorphism on the cohomogeneous group. So actually, I only need to consider the cohomogeneous group of this kind, H, the equal degree, HRI, the by degree the same. Then their results, Gromov and Yomedin result tell us that the topological entropy equal to the right hand side, this algebraic invariant. So if you look at the right hand side, this is a this is so-called the spectral radiance of a certain linear operator, and this is the direct sum of a cohomogeneous group. So and this is a split. So it is actually equal to the logarithm of the maximum of these spectral radiance of the pullback action of F on HRI. So we just need to look at HRI. So we know that this coordinate group contains the algebraic cycles of codimension I. So we just need to look at this small group. So so from here now we can define another invariant by this quantity. So we call this number the dynamic degree. So this is a very important invariant in algebraic dynamics. So it's so important. So it appears everywhere. So let me just recall the definition. So for this still d-dimensional variety, and the case dynamic degree denoted by lambda k of f is just the here the spectral radiance of this pullback action. On the other hand, it also equal to the pullback action of f on this group. This group is in makes sense in algebraic geometry for algebraic varieties. So it's just the this group is just the happening group of algebraic cycles of codimension k modulo numerical equivalent. So it's a finite generator uplink group. You tensor with R, you get some vector space. In general, we know that if you assume standard conjecture D, then this group is embedded into HKK. But anyway, we don't need that. So on that, also equivalently, this number is also equivalent. Equal to the limit of this nth root of certain intersection number. So this intersection number means that you choose an arbitrary ample divisor hx on x, and then you look at the pullback of this iteration f up to n on hx to k, and so this kind of algebraic cycle, and then you times the complementary degree algebraic cycle, so hx to the d minus k, then this insane number will goes to infinity in general. So when n go to infinity, then look at the nth root, the growth rate of this insane number. Then it gives us the dynamic degree. Okay, so now you see that the topological entropy is equal to. Sorry, any question?
Fine.
Topological entropy is equal to the logarithm of maximum of all dynamic degree. Okay, and then as I said, Umedin and Gromov result tells us they are equal. So in fact, Umedin proves that the topological entropy is bound below by the algebraic entropy. So this is so-called Schub's conjecture in 17th. So Umedin solved this conjecture in 1987. So 10 years earlier than Umedin's result, Gromov so he first proved that the topological entropy is bound above by the dynamic degree. So he first proved this inequality. So the idea is that he introduced another invariant called log f, and then he showed that at top is less than equal to log, and log is less than equal to hx of f. So let me tell you what is this log. So this is so-called the volume growth of iterated graph, and this invariant. So the volume growth, let me first look at what is the iterated graph. So given a dynamical algebraic dynamic system, or in general arbitrary dynamic system, so we can look at this called iterated graph, which captures all information about this dynamic system. Because when you look at a dynamic system, in general, you need to look at the iterations. So this iterated graph basically means that you look at the iteration up to a certain level. For example, you just look at this induced morphism f comma f square up to f to the n-1. This kind of product morphism. So it maps it is from intercept point x to this x to the n minus 1. So the image is given by coordinate. Okay, and then you look at the graph of this induced product morphism. So the induced graph lies in x times x to the n minus 1. So it's in this product space, x to the n. And still, because it's defined on x, so this gamma n still has dimension d. D is the dimension of x. So this iterated graph as a graph of this morphism is actually a d cycle in x to the d. Oh, sorry, x to the n. Okay, and then Gromov just consider the volume of this gamma n, or in other words, in algebraic geometry, it's just the degree of this cycle, degree of this d cycle in x to the n. So we look at the degree is we choose this polarization. So we first fix a arbitrary ample divisor on x called hx. Then we look at this kind of a lateral ample divisor on this product space by just the pullback of this pi I. I mean, we take all pullbacks and take the sum. So this is a lateral ample divisor on x to the n. And then we look at the degree of this gamma n or volume called by Gromov of the gamma n. So gamma n times the d's power of this ample divisor, because the gamma n is a d cycle. Okay, so this is the volume of gamma n, and then the log of f is just the exponential growth rate of the volume of gamma n. So by definition, it's just the limit soup of log of volume gamma n divided by n. So this number means the exponential growth rate of volume gamma n. Okay, and then just use certain projection formula. We can show that the volume of gamma n is also equal to another intersection number. So here, this intersection is taken in x x to the n, right? And then you use the projection formula, you can go back to x itself. So it is equal to this intersection number. So the top self-intersection of this divisor, this divisor is a divisor on x. So it's look at the pullback of these iterations on this hx and take the sum. Okay, so so now I denote this divided by delta n. So delta n is this sum, the sum of these n divisors. Okay, then the volume of gamma n is just the top self-insertion number of delta n, this divides on x. Okay, so this is the definition of log of f. So I just say that Gromov proved that we have this inequality. So now I'm interested in zero entropy automorphism. So which means that all invariants vanish. So all of them are zero. So h top is zero, h egg is zero, log of f is also zero. So in this case, we can consider another invariant. So because the law of f means the exponential growth rate of this volume, right? So now we can if f has zero entropy, then we don't have exponential growth. So it grows slowly than exponential. So we may expect that there might be polynomial growth. So this is introduced by Sergio and Paris Maskovich in 2020. So they defined this so-called polynomial volume growth denoted by Polov f. So basically, just the polynomial volume growth of this iterated graph gamma n. So we look at the volume of gamma n and then consider the polynomial growth rate. Then this is a natural definition. Okay. So here is a remark: if f is zero entropy, then equivalently the all dynamic degree is 1. and the first dynamic degree is also 1. This is also equivalent to the first dynamic degree being 1. This is by the log concavity property. Also, because if you look at lambda 1 is actually just the spectral radiance of F, the pullback action of F on the Lorentz group. So this is algebraic. This is defined. The characteristic polynomial is has an integer coefficient. So all roots are algebraic integer. So if the spectral radiance, the maximum is 1, then by Kronik's result, we know all eigenvalues are roots of unity. Since all eigenvalues are roots of unity, then we know that this action, or this pullback action, is actually quasi-idempotent, which means that up to a certain power, like for example f to the n, the pullback is just the unipotent. All eigenvalue are 1. On the other hand, you can also check that plot of f, this invariant is independent of the choice of the ample divisor. So this is not hard to show. Moreover, the plot of f is also equal to the plot of this invariant is also equal to the plot of f to the m. So no matter you choose, you can iterate this f to any power. Then the plot of f is plot of f doesn't change. It just measure certain growth rate. Okay, because of this lemma or this remark, now we can, if you consider a zero entropy automorphism, we can always assume that the pullback of f on the Lorentz group is unipotent, because we just replace f by f to the n. Then the plot of f doesn't change. Okay. This is the motivation. This is the first motivation to consider the plot of f. Another motivation is that this plot of f, this invariant, is also related to another so-called Gaussian dimension in non-commutative geometry.
And can you remind, please? So this fact that it doesn't change if you replace f by the power of f. And what happens if it was just a usual logarithmic volume without p, just log?
You mean this part, right?
Yeah.
It's not a you need to work a little bit, but it's not so difficult. You just write down. You just consider compare this delta n, like because if you replace f by certain power, you get another delta like delta nm, and you just compare these divisors, then use certain positivity to compare delta nm and delta n, something like that.
But the question is that how does the usual logarithmic volume behave if you replace f by f to the power of m?
The usual volume growth.
The usual logarithmic volume without p.
Without what?
Without letter p, like LOV of f.
Oh, just the law of f, right?
Mm-hmm.
So you mean here?
Mm-hmm.
I guess here. Oh, I know your meaning. So I guess here it doesn't change either. It doesn't change. So here is the iteration. So here is the iteration. So this is iteration, not the product. So if you consider the product system, then of course the entropy will be the multiple. Okay, but if you just look at the iteration, then this doesn't change.
So the entropy doesn't change under iteration.
Yes.
I see. Thank you.
Yeah. Okay. Okay. So I just said another interesting point is that this plot of f, this invariant, this is actually a purely algebraic invariant, algebraic dynamic system defining in algebraic dynamics. It also related to the so-called GK dimension. So this is introduced by Artintet and Vandenberg in 1990s. So they consider this so-called twist homogeneous coordinate ring. So this is a kind of a twist version of a Euro homogeneous coordinate ring. So which is twisted by automorphism F. So which means that we look, for example, giving a smooth project variety X and automorphism and ample line model, we consider the direct sum of Bn. So here Bn is this is a common group, just the group of all group sections of this line bundle. So L tensor with F pullback L tensor with F square pullback L, and so on. And then there is a natural definition for multiplication defined in this way, so that the direct sum of Bn, the capital B, is non-commutative. Okay, so we get a non-commutative algebra. And then for in general, for arbitrary non-commutative algebra, we have this so-called Gavin-Kirian dimension. So this dimension measures the growth of this algebra. Okay, so for example, if your algebra is a commutative algebra, then the GK dimension is just the usual crude dimension of this commutative ring. But if you if B is, but here B is non-commutative, then there is certain way to define the growth of this algebra, just like the growth of groups. Okay, so for example, if you have a group G, you can consider the group algebra of this group G, and then the growth of this group and the growth of this group algebra as algebra, they are the same. So this GK dimension is the generalization of growth of groups. So anyway, the Killer in 2000, so he proved that GK dimension of this non-commutative algebra B, the twist homogeneous coordinate ring, is finite if and only if this pullback action, the pullback of this automorphism on the Lorentz-Serveri group is quasi-important. So in other words, using in algebraic dynamics, it means that F is of zero entropy. Okay. So GK is
sorry, a question. In your definition, F is automorphism. Can it be endomorphism?
No. So here, if F is endomorphism, not automorphism, is a non-invertible endomorphism, then F must be of positive entropy. So when F is of a positive entropy, then polar of F must be infinity, cannot be finite. Because when F is of positive entropy, then the growth of a volume is exponential. So if you okay, right? If you consider the polynomial growth is infinity.
Yeah, but still definition works, right?
Yeah, definition works. Yeah, of course. So so here means that if you consider F is the endomorphism, then not is positive entropy, then polar of F is infinity. Because this log volume gamma n divided by n is a finite number. So if you divide by log n, it's infinity. So Killer he also proved that the difference of the two invariant is just one. So this is why I said they are equivalent. So you don't need to distinguish two invariants. So they are almost the same. Anyway, so moreover, so he also proved some give some control for this GK dimension. So now we assume that the pullback of F on the Lorentz group is unipotent because we can replace F by its iteration, so that it's not just a quasi-potent, it becomes unipotent. So in other words, you can write this operator as just a identity plus some Leopotent operator. I use this n below the nilpotent operator on the Lorentz group. And moreover, by the definition, the polar of f is the volume growth of iterated graph. It is also equal to the volume of iterated graph is equal to the top self-insertion of this divisor delta n. So I recall delta n is defined as the sum of these n divisors. So now f is 1 plus n. You replace f by n plus n, and you expand this term, we will get this sum by binomial theorem. So we have this sum, then we exchange the sum. We switch the sum, then we will have this term. Okay. So now the interesting thing is that we have some binomial identity saying that this sum is equal to just one term. So n choose I plus 1. Okay, so here m choose I. So m is from I to n minus 1. Then the sum equal to n choose I plus 1. So here this is so-called hockey stick identity. So why we have this identity? There's many ways to prove this one. For example, by induction, but there is an easy way to explain that. So because both sides means certain both sides means the numbers of certain like non-negative integer solution of these kind of equations. So if you look at, for example, if you look at this equation, we know that by some combinatorial trick, we know that the number of the positive solution is m choose I, and the number of the first inequality is n choose I plus 1. So now you see that this m could be I plus 1 up to n minus 1. So then you see that these two are the same. Okay, so using this identity, I'm sorry?
Why is it hockey stick?
Why is it hockey stick? I don't know. Sorry. Yeah, yeah, it's an interesting name. I don't know why they call this give this lambda in this way. Anyway, so using this identity, the advantage is that so at the beginning, this delta n is the sum of n divisors, and the n will go to infinity because we look at the growth. So here n will go to infinity. But now this is a finite sum of k plus 1 divisors. Okay, because we have this nilpotent operator. The n to the k plus 1 is trivial. So I forgot to assume that because n is a nilpotent operator. Yeah, so n is a nilpotent operator. So I assume that the nilpotent index is k plus 1, which means that n to the k plus 1 is trivial, is 0, but n to the kth power of n is non-trivial. Okay, so now this is the final sum. Then the key lemma is the following. This lemma due to Killer, so he didn't write it precisely, but the idea is there. So Lin, August, and John, they formulated the lem as follows. So polar of f is equal to the degree of the polynomial of this polynomial. So we map positive integer n to this intersection number delta n to the d. So delta n, like I just said, is the final sum of this divisor. So you take the d's power, the top self-insertion. Okay, so now you have k plus 1 divisors, then d's power. I don't know, but it's just somehow it's useful to expand this power as a large sum. So we expand this sum, this product, so as this sum. So we have certain multinomial coefficients, and then we have this term. So just like we choose EI copies of this divisor. Okay, so we have this polynomial. So maps n to right hand side. So recall that right hand side the only term containing n is n choose I plus 1. So if you look at right hand side, so this term, the degree of n is if you look at this term, the degree of n is ei times I plus 1. So here I plus 1 times ei, and you take this product, means that we take the degree, the sum of ei plus is I plus 1 times ei. So right hand side, in this assignment, each term has a degree sigma I plus 1 ei. And then, but we don't know. So here, this is a huge sum, and maybe there's some cancellation because this divisor is this divisor. We don't know any positivity about this divisor. So we only have this kind of inequality. So there is a natural upper bound. The polar of f is less than or equal to the maximum of all these numbers, such as the intersection number. This intersection number is non-zero. If this intersection is 0, then we don't have this term. So this term disappears. So we don't need to look at this term. So we just need to look at these non-trivial terms. Okay, because this is the sum of all EIs is D, so we can take this D out here. So then polar of f is less than or equal to D plus the maximum of this set. Okay, so here is using this lemma Keeler. So he proved in 2000 that polar of f is less than or equal to D plus K times D minus 1. So he shows that this guy, the maximum of this set is less than or equal to K times D minus 1. So this is his first result. So he give upper bound. So let me just give you an example, show you how to use this lemma, use this lemma to prove some upper bound. So let me look at lower dimension case. For example, the dimension of x is 3. In this case, I assume k is true. Okay, so which means that the pullback of f on the non-separate group is unipotent. The nilpotent index is 3. So n to the 3 is trivial. So first, we can easily show that n square hx. So this divisor. So this is a divisor on x on threefold x. So we can show that the top self-insertion of this divisor is 0. The reason is that to show this divisor is the insertion is 0. We look at another divisor. So we look at this divisor. So we look at the square of n square hx times n hx. So by the projection formula, when f is the automorphism, so this insertion number, the left hand side is equal to f pullback n square hx square times n hx. But now f star is 1 plus n. So then we have the left hand side equal to the right hand side. Now right hand side have 2 terms, but you see that this 2 term, the first term is the same. Then we will get the vanishing of the top intersection of n square hx. Okay, so in this way we can show that n square hx cube is 0. So you see that in this set, when this sum is the largest one, then the insertion is 0. So then we can keep just do another one. We'll keep going. We can show that this divisor is also 0. N square hx square times n hx is also 0. The reason is similar. We again look at n square hx square times hx. Then by the same trick, we apply f star to this initial number. Then we have because n square hx is f invariant, so it doesn't change. But the hx will become hx times n hx. Okay, and this term will cancel each other. Then we see that we get the vanishing. Okay, then we can keep going. We can also show that this guy is also 0. I don't I won't write the details, and you can just use this trick. You can keep going. So n square hx square times hx is 0, and also n square hx times n hx square is also 0. Also n square hx times n hx times hx n hx square, all of them are 0. Okay. Yeah. So then you see that the first non-trivial is this kind of initial number is n square hx times hx square, or n hx square hx. This kind of divisor, these two initial number are non-trivial. So in other words, the polar of f is less than or equal to d. In this case, is 3 plus 2. So this 2 means that you have this 2. Here is 0, so it's 2. The multiplicity is here. Here you have 2, but here is 1. So 2 plus is 2 times 1. You have 2. So for this kind of because we have this we consider this sum of IEI. Okay, so this is why we have this kind of upper bound for polar of f. So polar of f in this case is at the most 5. So actually, in dimension 3, we know there is so actually in dimension 3, we now know that the only possible value for polar of f is 3, 5, and then 3, 5, and then 9. When k is 0, polar is 3. When k is 1, polar is 5. Sorry, k is 2. When k is 4, polar is 9. So k is always an even number. I will explain this later. So moreover, so a few years ago, in Lin, Augusto, and Zhang's work, so they prove that the polar f, they improve Keeler's result by showing that polar f is less than or equal to k times d minus 1 plus d minus 2. So their idea is to use their earlier joint work with Ding. So using so-called dynamical filtration. So in particular, in their journal, they show that k is at most 2 times d minus 1. There is the upper bound, universal upper bound, just in terms of dimension for this k. So for this result, actually, I checked the literature today. I found that so actually in 1980, another Russian mathematician, Giza Turin. So he first showed that for rational surfaces, the k is at most 2. Okay, and then later in 90s, this was generalized by Serge Cantat to arbitrary surface. So Cantat shows that for surfaces, k is at most 2. So now in their journal work, so they show that k is at most 2 times d minus 1. So now here's the question: Kantar and Paris-Mascovitch also in Lin, August, or Zhang, both of these two groups, they ask whether plot of f is less than or equal to d squared. If d squared is the upper bound for plot of f. So actually, d squared, if d squared is if plot of f is less than or equal to d squared, then this must be optimal because they have shown that plot of f, they give example by this complex torus. The plot of f is d squared. Okay, so now in my journal work, so we actually answered their question. So here is our main result. So let X be a smooth project variety of dimension D. F is the automorphism of zero entropy, and I assume that the pullback of F on the Laurent group. This is so now know that this is quasi-important. So I assume the maximum size of the Jordan block of the Jordan canonical form is k plus 1. So this is just means that if f the pullback is unipotent, then the nilpotent index of the nilpotent operator is k plus 1. So they are equivalent. And then we show that plot of f is less than or equal to this number, half k plus 1 times d. So if you recall that in Dean, Lin, August, and Zhang, they show that k is less than or equal to 2 times d minus 1, right? So if we combine our inequality with this inequality, their inequality, then you see that the plot of f is less than or equal to d squared. Okay, so now let me just explain the idea of our proof quickly. So here, so first, any question? So here, first, Kira, so he observed that this integer k must be even integer. This is the reason is that if you look at the this automorphism f, you can also consider the inverse of f. So if you look at this k is the degree growth of f, so the degree growth must be positive. So if you look at the f inverse, then so this k must be a even number. Oh, anyway, so now let's look at the proof. So by the key number I mentioned before, so to prove this inequality, so we just need to show the following vanishing result. So we just need to show the intersection number. This intersection number is 0, as long as the sum of EI is as long as the sum of IEI the sum of IEI is larger than half dk. Okay, so remember in our in that example, when kd is equal to 2, 3, as long as this number is very large, then the intersection number is 0, right? So now we found that this kind of half dk is a gap. So once you close this gap, then we don't have any vanishing. But as long as this sum is larger than this gap line, then all intersection numbers vanish. Okay, so now let me so we prove this one by induction. So first of all, when this sum is the largest one, which means that when this sum is the largest one means that the sum is just a dk. In other words, this EI we only have ek. We in this sum we have so we have sorry I will provision by induction later. So let me not first introduce a new notion called the partition. So here we have some we have this so-called restricted partition. So we can view this we use this kind of this means that we have ek copy of k, e1 copy of 1, and so on. So this is the sum of this is kind of a partition of the this sigma I. So now the recall that a restricted partition. This means that for example, lambda is a restricted partition. If sigma lambda I is n, and each lambda I is of course non-zero, is non-negative, and at most k, and we have d numbers. So then we call lambda is a restricted partition of n into at most d parts with each part at most k. Then we denote by capital PKDN. This is a set of all restricted partition with respect to the fixed KDN, and the little KPDN, little p KDN is the cardinality of this capital P. So it's a final number. So this number, little p KDN, is called a restricted partition number. So then this number, they are very important in combinatorics. I don't know any point. I don't very few combinatorics. I just check literature and find that this number satisfies the following properties. Like if you look at so first there's some generating function. The generating function is so-called Gaussian binomial coefficient. So in particular, if you let Q be 1, then the sum of all restricted partition is equal to D plus K choose D is a binomial coefficient. And they certify the same symmetry like binomial coefficient. But the most important property and also non-trivial property is this so-called unimodality. So this restricted partition number satisfies this so-called unimodality. So PKD 0, so here PKD 0 is 1, KD1 is 1, and so on. So it grows up to PKD half DK, something like that. It depends on the parity of D and K. But this, so you have this is the largest one, and then you're going down. So you first going up, and then you're going down. The middle point is given by half DK, or it's the integer part. So this is the unimodality property of the partition number. So why this one is related to our work? So we will see the later. So now we denote for each restricted partition lambda, okay, in capital PKDN. So we consider the following intersection number. So this intersection number. So this is the intersection number we are interested in. So we denote this intersection number by V lambda. So now we claim that V lambda is 0 for any lambda in PKDN. So it's a restricted partition of n. As long as this n is larger than half dk. So as long as this n is larger than this half dk. So you see that the half dk is just the so because this partition number that satisfies unimodality. So this is why we have this half dk. So now we prove this claim by induction, okay, by backward induction. So first, the trivial case, the first case is when n is equal to dk. So this is the first case. When n is equal to dk, then this means that we consider when n is dk, we want to show v lambda is 0. So here the v lambda is just so in this case, V lambda is just n to the k hx to the d. So this is V lambda. So to show this number is 0, so just like the example I gave before, we consider another integer number. We consider this integer number. No, sorry, this integer number corresponding to another partition in PKDn-1. Okay, so we look at this initiation number. So it is actually just the d-1 product of nkhx times n to the k-1 hx. So look at this initiation. Then we apply f star, because f star is 1 plus n. So this is f invariant. This guy will become 2 terms, and the one term, the first term is the same. So the first term is just the same. Then we will have this v lambda is 0. So we have this v lambda is 0. So this v lambda is nkhx to the d. Okay, so now by induction we fix the arbitrary n such that n is greater than half dk, less than dk, and we assume that as long as this lambda is a partition of m, where m is greater than n, then v lambda is 0. So this integer number is 0 when lambda is a partition of m is greater than n. So now we just need to show that when m is equal to n. So in other words, for any partition of n, the v mu is 0. So this is just the induction. So to show v mu is 0, so now mu is a partition of n. So recall that if you want to have some vanishing of this integer number, so here mu is in n, is a partition of n. We decrease. We look at another partition of the n decreased by 1. So we look at a restricted partition lambda, which is the partition of n minus 1. Okay, so then similarly, we look at the v lambda. V lambda is this insertion number. Then you apply f star and you do some algebra. Then you will see that finally this first term will be cancelled. The first term v lambda will disappear. Then you will only have this term. This is the second term, the sum of ei v lambda I. So here lambda I is this lateral restricted partition from a given lambda. So recall that lambda is the partition of n minus 1. You will write lambda as a k 1 ei 0 ei. So lambda I means that you increase just 1 I by 1. So you replace 1 I by I plus 1. So which means that now you have ei minus 1 copy of I, but you have ei plus 1 copy of I plus 1. So you just replace 1 I by I plus 1. And then the remaining term, you have a lot of complicated integration numbers, but all of them will corresponding to a restricted partition such that this is partition of m is greater than or equal to m plus 1. So by induction, this is 0. So by induction, this is 0. Okay, then we have a linear equation. So now we have a linear equation. The sum of ei v lambda I is 0. So now we in summary, so now we know that for any restricted partition lambda of n minus 1, we will have an equation. So here for this equation, this lambda I is a partition of n. Okay, so now we will have kind of little p k d n minus 1 equations for little p k d n variables. So this kind of a larger homogeneous system. So now we have this system. So this time the coefficient matrix is in this space. So the size is eta p kd n minus 1 times eta p kd n. So this is not a symmetrical is not a square matrix. Okay, so just to solve linear equation, so we have this linear equation. Now the problem is that so we want to show that v mu is 0, right? So the key is we want to show v mu is 0. Then we just need to show that the coefficient matrix has a 4 rank. We just need to show the coefficient matrix has a 4 rank, and the coefficient matrix is defined in this natural way. I don't have time to explain, but the key point is that we managed to show that this is our second main theorem. So we show that this coefficient matrix AKDN, all these matrices are of 4 rank. Okay, so this rank equal to the rank of this matrix is equal to PKDN when n is large. It is equal to PKDN minus 1 when n is less. So this kind of the gap line. So the middle line, because the restricted position satisfies unimodulity. So I think the idea to show this one. So I saw at the very beginning I calculated by hand a lot of this matrix, and then I checked by Mathematica. I found that all of them they are of 4 rank, and then sometime later I Google a little bit, and I found a code. So I got a code, and then I found for this k like at the most 20, d at the most 30, something like that. So all of these rank, all of these metrics, they are of 4 rank. Then I can think then I think we should prove this one. It should be true. So the idea of the proof is very simple. So I can explain in one word because I don't have too much time. So to prove this matrix of 4 rank, so the idea is that we realize this matrix is AKDN as representative matrices of Lefschetz objects of Lie algebra SL2C representation, and then we use this the Hart-Lefschetz type theorem for this Lie algebra representation. Okay, so I just give you show you this diagram. So which means that we consider SL2 Lie algebra SL2. So then recall that for this Lie algebra SL2 we have 3 generator. Okay, and then we consider representation, and then we will have like a chain. So for example, we go from this operator y. It maps this eigenspace v mapped by dk minus 2n, then so maps this space to v dk minus 2 times n plus 1. So this is the operator y, and then we found that this operator y corresponds to our matrix. So our matrix is A, the transpose of our matrix. And then because this you can easily check that this is the commutative diagram, and then so our matrix is realized by this Lefschetz operator y of this Lie algebra representation. So then we are done. Okay, I think I just stop here. Thank you.
Thank you. Okay.
Thank you.
Actually, I have a couple of questions. Can you return back to the bounds, to the lower and upper bound on the value of Plov?
Can you repeat the question again?
Can you return to the lower and upper bounds?
Lower we not give upper bound. You mean the lower bound?
Well, yeah. When you have the statement of the bounds.
You mean
Yeah, in particular
the lower
here.
bound.
And so you said that the upper bound in certain cases is achieved like this d squared by on the complex tori. And do you know
Yes.
something about how sharp is the lower bound?
How sharp a low bound? Okay, this actually my last slide. So we suspect that the lower bound might be look like this number.
And so this you believe to be sharp.
Yeah, this is sharp. This is given by Abelian variety by complex tora. For complex tora, we have this lower bound.
And what about, and can you say again, what about the upper bound? You have d squared for the complex torus.
Yes. So you see here, so we prove that our main result is prof f is less than or equal to half k plus 1 times d. But we now know that k is at most 2 times d minus 1. So
this
will
makes
combine
d squared, exactly.
Yeah, d squared is the upper bound.
And this is achieved at least for complex tori.
Yes, it can be achieved by complex tora or Abelian variety. So the easy example, the easiest example is you just consider Abelian variety just the nth power of a Euclid curve. And then you consider the automorphism is given by just the maps coordinately. Something like this one. So just look at the unipotent, the standard unipotent matrix. So e to the d. Okay, then we can show that the proof of this automorphism f, if f is this guy, then proof of f is d squared.
I see. And also, when people study dynamical degrees in dimension 2, I think that the situation is roughly like as follows. So for convex tori, things are relatively simple, and the really interesting cases are rational surfaces and K3 surfaces. And what happens?
Right. You
What
are
happens if
right.
you restrict to rational varieties in high dimension? What do you know about the bounds if you restrict to rational case?
Yes, so we know that, for example, if for surface, if you have an automorphism of positive entropy, then this surface must be rational surface, K3 surface, Enriquez surface, or Abelian surface. And the Abelian surface is easy to construct. So the interesting case is actually the rational surface, like P2 block at least 10 points. So yeah, so that's the most interesting part.
Yeah,
and I think this has been studied by Curtis McLaurin.
Yeah,
so
I know this, but my question is, in our discussion of this plov,
for plov, no,
yeah,
for
suppose that
plov,
you
this
restrict
is
to rational
another thing.
case.
Yeah, for plov, because plov, you have to assume the automorphism is zero entropy. Otherwise, plov is infinity.
I understand this. And what happens if you ignore all varieties except for rational ones? Do the bounds become, what do you know about the bounds in this case?
So if I remember correctly, in their work, so they consider they give some, for example. So for example, we want to they want to construct some examples such as the plov f is maximum, like d squared. So now we now know the abelian variety could give us some example, but they also show that for rational variety, we can also have this maximum number. Even for Calabi-Yau variety, we can also have this example. Even for quadratic dimension 1, something like that. So this means that this invariant is not sensitive to quadratic dimension. So it kind of in many quadratic dimension, we also have a lot of examples.
So this makes some difference between with the degrees. So this makes a difference.
Yeah, right.
And maybe the final question. So the correct maybe an analog of K3 surfaces is hyperkähler varieties in high dimensions. What happens if you restrict to hyperkähler case?
In hyperkähler, they also consider hyperkähler variety already. I think they prove that for hyperkähler variety, they have considered this case already, but I don't quite remember the precise. But you cannot achieve the maximum. This should be true. You cannot achieve maximum.
So the bounds are going to be stronger.
Oh, I now remember that because you can for hyperkähler variety, so you can just consider the initial form which looks like surface. So in this sense, you can even show that this number k for hyperkähler variety, it might be just at the most 2. So in ours for hyperkähler variety, this plot f you might only have two possibility. So either plot f is equal to the dimension or 2 times dimension, something like that. So plot f is equal to d or 2d.
I see. Thank you. I see. Thank you. Okay. Do we have any more questions?